All right, let's move on. So the next question is, well, how do we reasonably measure how big a matrix is? Okay, and there are ways of coming up with sort of artificial ways of measuring how big a matrix is. And then there are ways of saying, well, but what is it really that we're trying to measure? And all of a sudden you end up with a class of matrix norms that are much more reasonable. So, first of all, what is a matrix norm? Well, you can do exactly the same thing. Let nu be a function from n by n. So this is the set of all matrices to the real numbers. Then it is a matrix norm if for all a, I should start erasing. A and B in C n by n and alpha in C. A not 0 means its length is greater than 0. If you multiply A by alpha, then you just get that. And if you add two matrices together of the same size, then you get this right here. Fair enough? Now, one way to create a class of matrix norms is to do something that maybe to computer scientists is actually very natural. Okay? You say, look, if you have a matrix A, you can think of this as just a bunch of columns. Now, when we store A, we need to take a two-dimensional array and map it to one-dimensional memory. And one way of doing that is to say, oh, we'll just take A and store it one vector on top of the other. Right? We could think of this just as an array of numbers, and we could then just think of it as actually the vector that you get by stacking them on top of each other. And if you do that, and then you take any of these vector norms and apply it to this, you actually get a matrix norm, and that's pretty easy to prove. Okay? So you could then say, look, why not define the matrix 2 norm as the 2 norm of all of this? And if you did that, what would that really be? If you think about it carefully, it's really the same thing as taking the sum of the squares of all of the elements in A and then taking the square root of that, right? I encourage you to think about it a little bit differently because it'll make your homework easier to grade. You can also show that this is the same thing as the square root of the 2 norms squared. Which actually makes it a little easier. Well, there are a lot of cases where thinking of it this way actually turns out to be a better thing. I'm not sure if right here. I mean, here it's whatever. Let's move on. But here's the curious thing. This is not what in our field we call the matrix 2 norm. Okay. This is what we call the Frobenius norm. And for completeness, let's actually write it out. It's the same as the sum from I equals 0 to n minus 1 of the sum j equals 0 to n minus 1 of ij entry squared, and then the square root of that. Okay? Now, why do we call this the Frobenius norm? It's easy to prove it's a norm. Well, it's because it has no physical meaning. Okay? And for that we need to go back to something that you hopefully reviewed if it wasn't immediately obvious to you when it was sort of mentioned last time. And that is the fact that matrix vector multiply represents a linear transformation. Okay, so let's go back to that. Let's erase this. A times x really represents a linear transformation L of x. L takes Rn into Rn. If you're not comfortable with that, go back to the massive open online course and read week 2 and week 3. Okay? Essentially what happens is that a column of A, what happens if you do A times the jth unit basis vector? This is the vector that has all zeros and then a 1 in the jth position. What happens when you do A times EJ? You got the jth column of A. So actually what happens is, if you're given a linear transformation, then the way you come up with the matrix that represents it is by feeding it the unit basis vectors, or the standard basis vectors. And the columns of A are actually how the standard basis vectors are transformed. All right? Now, given that, you shouldn't ask the question, how do you measure how big a matrix A is? You should ask the question, how big is a linear transformation? Well, the transformation transforms. Okay, so you really need to think about what is it that the transformation does to a vector. Well, it does two things. It points it in a different direction, and it stretches it. Okay? Now, pointing in a different direction, what direction a vector points in has nothing to do with how long it is. Well, actually, if you think about it, one norm and infinitive norm it probably does, right? I shouldn't say that. But the important thing is that it stretches. Okay? So, a reasonable norm is to say, how much does the linear transformation stretch an arbitrary vector? In particular, what is the most that a vector ever gets stretched by the linear transformation? Okay, now, how can we express that? Now I can erase this. This just means I'm going to spend the rest of the lecture trying to erase. There we go. So, what are we really saying? We're given a matrix A, and what we would like to do is say that the norm of that matrix is given by supremum over all x of A times x divided by x. Now, I'm leading up to the definition, okay? So we're not there yet. Can I take the supremum over all x like this? Better leave the zero vector out, right? So we'll do this. What is the supremum? Any mathematicians here?
It's the least upper bound.
What's the least upper bound? It's the least upper bound, yes. Isn't that just the maximum? No, because?
The supremum of the open, some sets don't have a maximum, like the open set, the open intervals, all the numbers less than 1.
Okay, so if you have the interval from 0 to 1, not including 1, the supremum of the absolute values over all of those is 1, but it's not in the set. If, on the other hand, this is a closed compact set, then you can say the maximum is attained, and then you use the language the maximum. We don't know yet if this maximum is attained, or the supremum is attained, and therefore as we define it, we better start by defining it with the supremum. Okay? So, now, obviously, we need to somehow measure this vector, so we would have to choose a vector, and this is a vector in Rn, and this is a vector in Rn. So, in all generality, you may have a measure for the vector in Rn, and it's different measure for the vector in Rm, in which case you then get a matrix norm that's induced by these two other vector norms, etc. You got it? Now, there's some interesting things. Well, one thing we know is that these are vector norms, and therefore all of these things here apply. And the nice thing, of course, is if x is not 0, then we're not dividing by 0, so that's a good thing, right? But we also know that this is equal to the supremum over all x not equal to 0 of a times x over right there. Okay? And why is that important? Wait a second, is that right? I can't just do that, right? Yes, because all I've done is I've used this right here. Right? And why is that important? Because then we can talk about it as the supremum over all y that have vector length equal to 1 in the new norm of a times the vector y in the new norm. Okay? And why is that nice? This is a closed compact set, which if you've taken real analysis, which is clearly not a prerequisite for this course, so just take my word for it. Okay. We know that a function over a closed compact set attains its supremum, and therefore we can now replace this by the maximum over all y with nu norm equal to 1 of a times y. Okay. The way to think of this is say, look, either you can think of this as take all vectors that are not equal to 0 and look at how much they stretch. But what do you really know? If here is our origin, and here we have some vector x, then by how much this vector stretches is merely a function of how long it is, because if you make this vector longer, then proportionally you get a longer output vector. Right? So the stretching stays the same. And for that reason, all you really need to do is look at how the unit ball, where the 2 norm this would be a circle, is transformed, which is what this definition says, which is then equivalent to the definition of the max over all x not equal to 0 of by how much it stretches. Get it? Now these are the useful norms. And you can do that in the 1 norm, the infinity norm, the 2 norm. You can prove that all of those are actually norms. And those are known as induced matrix norms. They're induced by the corresponding vector norms. And typically, you take this norm for this vector to be the same as this norm for this vector. So the matrix 2 norm is defined as the maximum over all x not equal to 0 of a x in the 2 norm divided by the 2 norm. Same thing for the 1 norm, same thing for the infinity norm. All right? Any questions about that? The Frobenius norm has no equivalent, okay? You can't sort of say, well, it stretches, okay? Yes, it's a norm, but it's kind of artificial. Now, it turns out that the Frobenius norm is very important, so we often will use the Frobenius norm in our discussions. The matrix 2 norm is important simply because the Euclidean norm is so important, and there are certain aspects of the 2 norm that will become very important, for example, when we talk about the singular value decomposition, because it has some relation to that. The matrix 1 norm and the matrix infinity norm turn out to be the ones that are easy to compute. Okay. The matrix 2 norm turns out to be really difficult to compute in general. All right? Any questions? Okay, so what makes the infinity norm and the 1 norm so nice? If you take your matrix A and you think of it as a bunch of columns, then it turns out that the matrix 1 norm, which is defined as the max over all x not equal to 0 of ax in the 1 norm over the 1 norm, and equivalently is defined as the max over all x with 1 norm equal to 1 of a times x, is actually also equal to the 1 norm of a, let's put a capital J there, where what am I saying here? You look at the matrix by columns. For each of the columns, you can compute for each of the columns, you compute the 1 norm. And you take the max of all of those. Now, why do I do it in such a cumbersome way? Because for a lot of proofs, you have to sort of say, let J be the index that maximizes, and then other parts of the proof sort of fall out. All right? Cool. How do we prove it? Yeah, well, let's have a look. If this were an undergraduate course on how to, I would simply say it is. Right? This is a graduate course where we want you to understand, and therefore we're going to prove it. Well, I haven't done that in a while, so let's have a look. Whenever you do a proof that involves a definition, you just kind of start going with it, right? So, now the first thing you do is you plug in the definition. And this is where sort of the real trick comes in these kinds of proofs, because which of the two definitions you pick will actually make your proof fall out much nicer. And so you can sort of say, well, how do I know which one to pick? And it's like, well, unfortunately, I don't have the answer to that. Okay? Which is where we sort of go, well, that's where experience comes in. Well, strictly speaking, there probably is some rule, but I haven't thought it through. I often think through very carefully why I do things. I'm a computer scientist. As a computer scientist, you try to make what you do systematic, so that you think to yourself, and therefore next time I'll just program it up so I'll never have to do it again myself, right? But I haven't done that for this. So, but from experience, I happen to know that this particular definition, is that the definition that will work better? Let's try it. If I'm wrong, then we just learn something, right? So we say it's the max of all x with one norm equal to 1 of a times x with one norm. Okay. Now, the claim is that this has something to do with the columns of A, right? So it would be wise to think of A times x, a formulation that somehow exposes the columns of A. So what we will want to do is say max of all norms equal to, all vectors with norm equal to 1 of the sum j equals 0 to n minus 1 of the jth element of chi times the jth element, the jth column of A. Bingo, we have something that exposes columns. Maybe now we can get somewhere. Okay, which is why it's really important for you to have learned to think of matrices in terms of columns and in terms of rows. You can get there by dealing with the individual elements. If you don't crazy, we will try to grade it. So let's not go there unless we have to. All right? Now we better come up with some kind of bound, right? Well, we know something about the triangle inequality. And therefore we can say, well, that's the less than or equal to the max over all x with norm equal to 1 of the sum j equals 0 to n minus 1 of the norm of chi j aj. You'd have some kind of note saying triangle inequality. Of course, applied several times, right? N times. N minus 1 times. Okay. Now we'd like to somehow get the maximum. So then we know that that's actually equal to the max over all x with one norm equal to 1 of the summation j equals 0 to n minus 1 of the absolute value chi j times aj. Right? Now we're getting somewhere, because if only this weren't here, what would this be? One norm of x. And we know that the one norm of x is 1, right? Cool. So what we really want to do is say that's equal to the max over all x with 1 equal to 1 of the summation j equals 0 n minus 1 times chi j times the maximum over all j of aj. Well, probably should say k here and k here, right? I did some unfortunate choosing of letters. And then you see, oh, but I can pull all of that out. This becomes 1, this becomes it. So now we have an upper bound. But having an upper bound is not good enough, right?
Shouldn't that be a less than or equals just before that? Between the
this should have been a less 3. Thank you. All right? Now, we want to show equality. We have a bound now. And the way you then show equality is to say, oh, but there is a vector that actually maximizes. So you start the other way. You say the one norm of A is equal to the max over all vectors with one norm equal to 1 of A times x. But that is greater than or equal to, pick a vector that actually has length 1 in the one norm. And you're putting in a specific vector, which then of course is bounded by the maximum. So you know that that's greater than or equal to some magic vector that you want to put in there. Well, somehow you want to pick out that column that actually has the maximal 1 norm. How do you do that? You do that with a vector that's a standard basis vector. So what you say is this right here. Okay. Which then is equal to, but J is the index, and this is where, okay, so J here is the index that maximizes flow by that quantity, therefore it must be. Get it? Okay, so for next time, I'm going to assign the rest of chapter 2. We'll have some exercises there, and you'll get lots of practice with these kinds of norms and their issues. All right? And what you see is that the 1 norm of A is bounded above by exactly that quantity. And is bounded